No, I'm actually not as tapped in as I could be, but I just talk a big game. Okay, so here's the deal. So on this plane here, let's make a shape. Have you seen this shape before? Yay. So you have a triangle here, right? What's this shape right here? It's a triangle, okay. So let's say I labeled this angle A right here. This is B degrees, and this is C degrees. And let's call this D degrees, D, E degrees, and F. What can you tell me about A degrees plus B degrees plus C degrees? What can you tell me about D degrees plus E degrees plus F degrees? You might know this, but you might not because you haven't taken geometry yet. But any idea? Does anybody know this? Matt, what is it? Yeah, it always equals 180. It always equals 180. So no matter how you change a triangle, the internal angles always add up to what? 180. Okay, that's great. Let's just remember that fact. Okay, so I'm going to draw a different shape now. Actually, I'm going to draw better. Do better here. What did I just draw? A sphere. So if this was the globe, you have the equator. I think it's the prime meridian is the vertical one. So it's not a bad sphere, if I do say so myself. Okay, so let's say you're walking on this. It's a perfect sphere. Let's say you're walking on the sphere. So if I'm standing right here, and I'm going to walk north, okay? Is that okay? I'm going to walk north. What's the angle right here? How many degrees is that? 90. It's 90 degrees. Okay, I'm going to keep walking, and eventually I'm going to hit the what all the way up here? North Pole. I'm going to hit the North Pole, okay? And then I'm going to turn, and I'm going to walk down. What angle is right there? 90. It's 90. You agree? I mean, you can kind of visualize this. I could rotate it, but you got it, right? I go down here, and I'm sure there's a name for this point right here, but I don't know it. And then I'm going to turn again. I'm going to walk back. What's the degree angle right here? 90, right? So I've gone from one point to one point to one point. So how many points did I walk from? The first point right here, to the second point right here, to the second point right here. Do you agree with that? So what shape is this? Do you agree? I agree with you. That's a triangle, right? Okay, so let's call this angle G degrees, I don't know, H degrees, and let's call that J degrees. How many degrees are in H? You already told me, 90. How many are in G?
How is that possible, though?
How many in J? 90, okay. We add them together, what do you get? What do I get? 270 degrees. But we just had a triangle. Wait. We just made a triangle, and these were all 180 degrees. You believe that. I'll tell you that it's true. By the construct right there, by the limits that you've set for yourself, it is 180. Here it's 270. What did I change? The shape. What is the shape? What shape are these on? Flat. What's the shape here? A sphere. It's a sphere. So here's the thing. On a plane, you are correct. On a plane, a triangle, the internal angles of a triangle always add up to 180. On a plane, always, right? On a sphere, do they have to add up to 180?
No.
What do you think they add up to?
270.
Always?
Most of the time.
But let's see. I'm kind of leading you here. What happens if I drew a smaller triangle right here? So I'm drawing that on the plane right there. Are these internal angles still 90 degrees?
Yeah.
They are?
Yeah, I think so.
Really? Does this look like it? I mean, I'm drawing a straight line here on the curve. Does that look like 90 degrees right there?
Well, is the scale the exact same?
The scale is the exact same, but I'm telling you, does that look like a 90-degree angle?
No.
It does not. Here's the thing. As you get the points closer together, the internal angles, the sum of the internal angles get closer and closer to what? What do you think? Exactly. On a sphere, the internal angles of a triangle add up to be at least what? At least 180. Because what you're saying here is these are less than 90, right? So the internal angles here add up to something less than 270. But can you ever get less than 180? No, you can't. So here's the thing. On a sphere, the internal angles sum to the internal angles of a sphere add up to 180, add up to greater than 180. Because can you ever get, on a perfect sphere, can it ever be totally flat? No. So if it's bent a little bit, it'll be greater than 180. So my question is 270 degrees the maximum that the triangle, the internal angles can add up to?
No.
How would you make it more than 270? Make the triangle bigger. Just simply look. So take this point right here and migrate it that way. Migrate this one behind like that, and migrate this one behind. So you're stretching that triangle over. Right? So do you see what's going on? I would stretch the triangle even more. So what happens to those internal angles G, J, and H? They get bigger than 90, right? Bigger and bigger. So what's the biggest? What's the largest sum, do you think? 360. Because if you pull them all the way back, eventually what are they going to do? They're going to connect, right? Eventually they're going to connect, and what are you going to have? All three are going to meet and form a 360 degrees. So the internal angles, it's going to be less than 360 but greater than 180 on a sphere. So here's the thing. You do geometry. When you do geometry in high school and a lot of college and calculus, generally it's on a plane. Then you get to multivariables on a surface. But once you start doing geometry on other planes, other places, not other places, but other places, the rules that you hold true start breaking. There's a great field of math. The field of geometry that you will go into first is called Euclidean geometry. Do you know what that's named? Who that's named after?
James
Yeah. Euclid. Did anybody know who Euclid was? Where he's from, when he lived? Euclid was Greek, lived 3,000 years ago. He wrote something called Euclid's Elements, like the first treaty on the oldest known treaty on geometry. Really important stuff was put down there, kind of first time published. We have parts of it. We don't have all of it. We actually recently discovered more of it, which is really cool. Do you know how they discovered more of his works? In the Middle Ages, it was paper really common? No, it was really writing material. Long-term storage of writing material was hard. So what sometimes monks would do is they would take texts that were no longer used and they would scrape off the ink, right? And then what would they do? They just write over it. They would scrape it off and then use that page for something else. Someone was doing a study of a medieval text, and what did they find underneath? They found some more Euclidean work. Do you have any idea what that's like? That's like finding an unknown Da Vinci underneath another famous painting. It's super cool. So they found it, but here's the thing. If there's Euclidean geometry, there's also non-Euclidean geometry. So Euclidean geometry is essentially everything that happens on a plane. Non-Euclidean geometry is everything else. So for example, in Euclidean geometry, one of the tenets of Euclidean geometry, two lines that are not the same line, if they are parallel, they never touch. In non-Euclidean geometry, guess what can happen? Lines can be parallel and touch. Here's another thing. Well, no, it's an oxymoron because you've never thought of things like on a plane before or on a sphere. For example, up until now, you thought that the internal angles of a triangle are always 180. They can be broken. So for example, let's talk about 3 dimensions. So in 2 dimensions, you graph things on the x and y axis, right? I could add in a third axis, and now do you see 3 dimensions right there? So you have forward and backwards, left and right, up and down. Do you agree with that? Okay, so now we're in 3 space. I could have a line going like this, and then above it, another line going like this. So I'm looking straight above these lines. These lines don't touch. There's one on top of the other. So if I'm trying to draw a sideways angle on this, let me see if I can. You would end up with a line like this and a line kind of like this, where there's this distance between them. So do you understand what I'm trying to draw there? Do these lines touch? No. Are they parallel? Do they look like they're parallel? No. In 3 space, you can have lines that don't touch, but they're not parallel. In 2 space, if 2 lines don't touch, what do they have to be? They have to be parallel. In 3 dimensions, you can have 2 lines. Like here are my arms. Are my arms parallel? No. Do they touch? No, they don't. They never touch. So in 3 space, there's lines can either intersect, they can be parallel, or these are called skew lines. In 3 space, so in 3D, 2 lines not touching, not parallel, equals skew lines. So here's the thing. There are a lot of definitions that you hold in your head that get broken down if you change little tiny things. Little tiny things. Does anybody know what velocity is?
Yeah.
Speed and direction. Speed and direction. So what that means is velocity describes, I could go 50 miles an hour that way or that way. Velocity tells you which way you can go. Do you understand that idea? Here's a fact for you to think about. That might be going over your head here. Can you instantaneously change velocity? Can you go from one velocity to the next instantly?
No.
No, you have to go through everything in between. Like in your car, can you go from 0 to 50 without going 40 miles an hour?
No, I knew it was parallel.
Yeah, you have to. Yeah, you can't. If you could, though, if you could instantaneously go from 0 to 50 miles an hour instantly, do you know what would be possible?
Everything.
Teleportation. Yeah. Yeah. Think about it. If you could change your velocity instantly, you could teleport. It's pretty cool. So let's talk about something else now. Okay, so here's another question for you. It's a classic question. If you know the answer, do not say it out loud. If you know the answer, do not say it out loud. This is a question where the answer is pretty much irrelevant. It's understanding why the answer is the way it is. Most of you have probably seen this, but it's a fantastic question to think about. The woman who either had or still has the highest measured IQ on the planet, this is one of her favorite questions. And here it is. It's called the 3 doors problem. It's pretty straightforward. Again, you don't say, the answer is irrelevant, understanding why. Okay, so you probably saw videos on it because I put a page up for it, but here's the basic idea. So Tori, you're on a game show, and behind one of these doors, we'll call it door A, B, and C, behind one of the doors, there's $1 million. You want the money. I'm just giving that out to you. Some people have played this game like, I don't want the money. You want the money, okay? You're trying to win the game. Behind one of the doors is $1 million. Behind the other 2, there's nothing, okay? So I know, I'm the game show host, I know which door the money is behind, okay? You get to choose one of them, but I'm not going to open it. Which door do you want to choose? Pick one. Pick anyone. Yeah, which door? Okay, so you picked B. So this is Tori's pick right here. Okay, I am going to open this door right here. And there's nothing behind it. So all you know, you've picked this one. I haven't opened B. Door C is still shut. But I've opened A, and there's nothing behind it. There's nothing here. Nothing. You now have the chance. Do you want to stay with your pick of door B? Do you want to switch it to C? And the question is, does it matter if you switch your guess? If so, why? Does it not matter? Or should you definitely stay? So there's 3 options. There's two options, really. Should you change your guess? Like, do you want to change it to C before I open it? Does it matter? Or should you stay the same? That's the question. And that's the overall question for this game. The question is, if you're in this situation where I open up one of the empty doors, does it matter? One last one here for you. Here's a really hard one. A really hard one. What shape is this? Or what am I trying to draw right here? If all these sides are the same. It's a square. Simple question. It is a rectangle. Yeah, sure. Is it possible to fill a square, completely fill a square, with all squares of different sizes other than the same square? So yes, I could take the same square and put it inside. I'm done, right? I'm asking, is it possible to fill that square with all squares of different sizes in a finite number, meaning not an infinite number? So you would think possibly yes, right?
Oh, wait. No, it's not.
Okay, you're like, no, he's trying to trick us.
Every single one of those different?
Every single square has to be different. It's different size. What do you think? Who thinks it's possible? If it's possible, what would I ask you to find? Well, no, if I asked you to find, if I said, if you wanted to say this square you could fill with all squares of different sizes, what would I want you to draw? All the squares, right? So I would want you to show me, like, okay, there's this square, and there's this one, and then there's this one, and there's this one, and then there's this one, and then, you know, I'd want you to actually show me a solution. Because could I check your solution? Sure, I could look at it and say, oh, you have filled it, so therefore, yeah, let me talk. Therefore, stop talking. Therefore, it is possible. But if you want to say it's not possible, it's much harder to prove it's not possible, because to prove it's possible, she only needs to come up with one example, right? To prove it's not possible, you'd have to use something completely different. So the question is, who thinks it's possible to fill a square of all different sizes with squares of all different sizes? 3 of you? Who thinks it's impossible? I'm not going to tell you. So the question is, what about a cube? Can you do the cube? Can you fill a cube? So what about a square? Yes, you can. What about a cube? Really, really simple game. Here's a game. Here's an infinite checkerboard, okay? It's just big. It just goes on forever, okay? It's just a grid. So here's the checkerboard. It goes on forever like this. You okay with that? Starts with a single piece. Here it is. One piece. There's only one thing you can do with that piece. You can pick it up off the board and replace it with a piece up here and over here. Any piece you can do that to, as long as the pieces above and to the right are free. So I'm going to take this piece right here, take it out, and replace it here. Can I move this piece right here? No, because there's a piece above it blocking it. So what do I have to do? Move this one. And then what can I do? Move this piece. So the pieces are expanding, right? See how they're getting bigger? Can I move this piece right here? No, because what do I have to do first? Move this one. But then I have to move this one right here, right? Right? Do you see what I mean? Now I can move this one. And now what can I finally move? I can move that piece. Okay, so do you understand the mechanics? Can't go backwards, you can only go forwards. I started with how many pieces? 1. So here's the game. You win the game if this space right here is empty. You win the game if that space is empty. So you either need to tell me how I make it empty, or if it's impossible, why it's impossible. You have an infinite amount of space. You can go on forever. So here's the thing. If you can tell me an algorithm, like steps you would take over and over again to do this, sure. Tell me how to empty that space. So can you play this game? Get a piece of paper. Not right now, but could you try playing this game yourself? Sure. I mean, do you see how they get, yeah, you get a whiteboard. So you see this piece right here? To move that piece, what do you have to do? You have to this one, this one, this one, and this one. But to move this one, it compounds really quickly, right? But you have an infinite amount of space, so you should be able to do it, right? I don't know. This is called, I call it the checkerboard problem. Checkerboard problem. I love this problem. It's a great problem.